And now we can talk about homework 10, problem 2. From the lecture notes, collect the definition of properties of stochastic processes as following. First one, we talk about wide sense stationary process. For the wide sense stationary process, it means it is constant and the autocorrelation is a function of time difference. Like if xt is a WSS process, then we can find that the expect of xt is a constant number, and its autocorrelation function is only is a function of tau. Tau is the difference of time. And second, we talk about independent increment process. Independent increment process means xt1 minus xt2 and xt3 minus xt4 on non-overlapping intervals are independent. And here are some examples. We can find that the Poisson process, the random walk, and the Wiener process, they are all independent increment process. It seems independent increment property is somehow related Markov process. And we can talk about Markov process. The Markov process means the past has no influence on the future when the present is known. We can write the definition of the Markov like if we have time S1, S2, SL, and M, m plus k. This all the integrals of time, and we can set a discrete random process xn. So the xn on m plus k, the state of xn on the time m plus k only related to the xnm is not has relation to the states before m. So that is Markov chain. That is Markov process. And we can talk about the fourth normal process. We also talk it as Gaussian process. So normal process, we can see a xt. A process xt is said to be normal if the random variables xt1, xt2 until xtn are jointly normal for any m. So the jointly density function of these random variables is like xn t1, t2 until tn. The jointly density function equals -1 This is the jointly function of these variables if these variables are jointly normal for any time. So we can see that the c in this function, the c is the autocorrelation over autovariance matrix, and the eta is the expect matrix. The statics of a normal process is completely determined in terms of its mean and autocorrelation function. So in general, we classified the normal process as a property of stochastic process. The normal process is a larger class of stochastic process. And the fifth, we talk about strict sense stationary process. Our process is said to be a SSS process if its statics is not affected by a shift on the time axis. So the definition of process is x1, x2 until xn equals this t1, t2 until tm equals fx x1, x2 until xn T1 plus epsilon, T2 plus epsilon, until Tn plus epsilon. This is the definition of the strict sense-stationary process. And number 6, white noise. The white noise process, we define the general white noise with the expect equals 0 and impulse autocorrelation function. If a process satisfies these two conditions, it could called a white noise. And here is an example: the Wiener process xt and the derivative of the Wiener process. Let's set the derivative function is Vt. So we can find the Vt is a Gaussian white noise with zero mean and impulse autocorrelation function. Gaussian white noise. Wt is Wiener process. And number 7, we talk about mean ergodic process. The definition is limit when t approaching infinity from minus t to t x t dt equals the expect of xt in mean square sense. And number 8, we can talk about martingale. The definition of martingale, we can see a martingale is a sequence of random variables for which the conditional expectation of the next value in the sequence is equal to the present value. Regardless values. And if we write this definition in math formula, we can write it as the expect of xt given xs equals x1 equals x1. So this is the definition of martingale.